Now I'm gonna walk you through on what happens that whenever you combine capacitors in different ways, okay? Whenever we connect capacitors in different way, we can have, we're going to start with two capacitors connected in series, okay? And and I'm going to show you what do I actually mean, what I actually mean about connecting capacitors in series. So we have here the representation of capacitors, right? In all those illustrations that we saw, you saw that the capacitor have two wires. Remember that? Let's go back here to Wikipedia, right? All those capacitors that you see here, notice that they have only two wires. One wire here, another wire here. This one has also wires can be connected to the ends. This one has two wires, two wires, two wires. Here, the wires are represented by those two connection holes, two wires, and so on. So when we connect capacitors in series, suppose we have two capacitors, we want to connect them in series, how do we do that? We connect one wire to the other wire, that's all, and we leave the other two wires on their own to be connected to a battery. At this very moment, I have two capacitors connected in series. Two capacitors connecting series, but they are not charged yet. They are uncharged at this very moment. Consequently, they have no energy whatsoever. Connecting capacitors in series. In order for them to become useful devices, we have to connect them to a battery. And that's what I have here. They are not connected to a battery yet because I put a switch right in here to prevent the capacitors from getting charged right away. Okay, here you go. The two capacitors. I put a switch. The switch is the same device that we use to turn on and off light bulbs, lamps in the classroom. The moment that we connect the switch, the electric charges of the battery that are here, they start flowing the circuit. Okay? This end of the battery is gonna have electric charge, positive electric charge flow to one plate of the capacitor. And those charges here that are on the negative side of the battery are going to flow to this other end of the capacitor. Here you go. Here the charge is being built up, right? But then something else happens too. These charges that you see right in here are going to induce or attract the negative charges to this plate of the capacitor and are going to repel the positive charges to the other side. And that's what's going to happen. The charges, the negative charges that are attracted, the positive charges that are repelled by this plate. And it works the other way too. Not only we have those positive charges being repelled by those positive charges of the capacitor, but those negative charges in the other capacitor are going to attract those positive charges and repel the negative charges. Okay? That's the picture that you must have when you connect two capacitors to a battery, to a source of energy, to a source of power. Okay? At this very moment, you know, up to this moment, all we have is the capacitance of the capacitor, C1 and C2. You know, at this very moment, the capacitors are discharged. There is no electric potential difference between them. There are no charges either. But the moment that we build up charges here, then we are going to end up with electric potential difference in the left capacitor, V1, and an electric charge that I will call Q1 as well. And C2, V2, Q2 for the other capacitor. Okay? Now there is a very important trick here, a very important piece of information. There are two important pieces of information. The first thing that you have to know is about this electric potential here. Recall that electric potential is nothing but electric potential energy. And in this circuit, you must have conservation of energy. Okay? And in order to have conservation of energy, the electric potential between those two plates must be, if the electric potential between those two plates is V, the electric potential between this plate and this plate must be V as well. Okay? And in order to have conservation of energy, the electric potential difference between these two plates here, V1, plus the electric potential difference between those two plates, V2, must be equal to V. That's the first important piece of information that you have. We figured that out only by using conservation of energy and by analyzing the circuit that we have. And that's what I have right here. What else is going to be the same? What else do you have to know? Okay, what else you have to know is that this charge here will in reality be the same as this charge. Okay? In order for something like that to happen, the amount of charge here, must be the same as the amount of charge in this other capacitor. Otherwise, there will be no, no stability in your system. So here you go. That's the next step. And that happens for capacitors connected in series. Two important pieces of information, right? For two capacitors connected in series, right, will be equal. And the charge on both capacitors will be the same. So, or, we're going to display that just in mathematical format. Like that. What else? What else can we do is that? Well, we can do the following. Now that we know that the charges in both capacitors are the same because they are connected in series, and that the electric potential of one plus the electric potential of two must be equal to the electric potential provided by the energy, we can come up with those. We can use the definition of capacitance to find out how Q, V1, V2, and C1, C2 are related to each other, right? C1 is going to be Q over V1. C2 is going to be Q over V2. That's the definition. We are applying the definition. Not only that, but we can also state that those two capacitors that you see right in here behaves as a single capacitor that will have an equivalent capacitance. Okay? So C1 and C2 ends up becoming equal to an equivalent capacitance. And the question that I'm posing is, what's going to be the value, the relation of this equivalent capacitance in terms of V, Q, C1, and C2? And that's what we are going to come up with. The procedure to find that out is rather simple. It's not that difficult at all. If you're seeing that for the first time, of course, it's always difficult when you see that for the first time. But once you get, you're exposed to it. We can write that down, that the equivalent capacitance is going to be Q, the charge must be conserved, right? Divided by V. Because the equivalent capacitance is connected, is the only capacitor connected to the battery. And then, what else? What else can we do? We can here write V1 as being, here from this equation, as being Q over C1, V2 as being Q over C2, and V as being Q over C equivalent. Now that we have this relation, we can use this relation as well. Okay, substitute V in there, substitute V1 there, substitute V2 there, and let's see what happens. Okay, we get this relation that we see right now. I didn't replace the Q over C equivalent yet, but now I did. Look what happens. The Q cancels out here in this equation. And we end up with this final formula. The inverse of the equivalent capacitance is equal to the sum of the inverse of the two capacitors. And by the way, for any capacitors that are connected in series, we have a similar formula. We have the sum of the inverse of the n capacitors. Okay? It's possible to prove, it is possible to prove that C equivalent will be always less than the smallest capacitance value in the set. Okay? It's possible to prove that mathematically. I want you to try to do that yourself on your own, okay? And again, if we want to connect capacitors in series, what do? You get this wire here. You want to connect those two capacitors in series. What do here? You get this wire here of this capacitor and connect to this lead. Or if you want to connect those two capacitors in series, you get this wire here and connect to this other one, and so on, right? This to this, this to this, this to this, this to this. That's how you get capacitors connected in series. And now we're going to work out what happens whenever you connect two capacitors in parallel. Okay? Going back to our drawing always helps us. Now we're going to connect two capacitors in parallel. This one goes elsewhere. Okay, we start with two capacitors, C1 and C2, and connect, okay, C1, C2, and connect them in parallel. That's how you connect them in parallel. They are initially uncharged, just like our capacitors that we end up connecting in series. In the case of capacitors connected in parallel, the two leads of the capacitor are touching each other. Okay? And then if you want to turn those capacitors into a useful device, we connect them to a power supply. The moment we connect them to a power supply or a battery, charges are going to migrate to the left, positive charges are going to migrate to the left side of the capacitor. And negative charges are going to migrate to the right side of the plates of the capacitors in the circuit. And then we have to figure out how the charges are, the net charges, and what are the electric potential. Because the two capacitors are connecting series to the battery, the difference in electrical potential between the two plates are going to be the same as that of the battery. It's going to be V. And then each one is going to have a charge 1. One is going to have a charge 1, right? Which one is it? Yeah. And the other one is going to have a charge 2. We do not know what those values of the charge, but we can calculate them if we know C1 and V. If you know C2 and V, just by using the definition of capacitance. Okay? The procedure is almost the same, but it's kind of that there is a small detail here that's different, right? Capacitors in series have the same charge. Capacitors in parallel have the same voltage. Capacitors in series, the voltage of capacitors in series sum up to be V. Capacitors that are in parallel have a charge that sum up to be equal to a net charge. Those two capacitors, just like before, they behave like a single capacitor that has an equivalent capacitance. The single capacitor has an electric potential V, okay, and a net charge Q. I'm going to do it this way. Like I said, those two capacitors in parallel, we can state that they behave like a single capacitor that's going to have an equivalent capacitance, an equivalent amount of charge, and an electric potential difference that's V. Okay? And by the way, this equivalent amount of charge, if you're going to, in order to have conservation of electric charge, this Q equivalent must be Q1 plus Q2. Okay? That's what this equivalent must be. The Q equivalent must be. So going back here, right? We start with two capacitors in parallel. We turn them, those two capacitors can be, we can state that those two capacitors behave like a single capacitor with an equivalent capacitance and also with equivalent electric charge. But because of conservation of electric charge, remember we have Q1 charge here and Q2 charge here. The charge of your equivalent capacitance must be equal to Q1 plus Q2. And because they are connected in parallel, the voltage is going to be V. Okay? Now let's see how this equivalent capacitance relates to the Q1 and Q2. Going back to our drawing here, two capacitors in parallel, connect them to a battery. The charge in both capacitors will be distributed among them. Because they are in parallel, we will have the following relation, V equal to V1, V2, right? And the capacitance of 1 is going to be equal to Q1 over V. Capacitance of 2 is going to be Q2 over V. The equivalent capacitance is going to be Q equivalent, and as I mentioned to you, Q equivalent is Q1 plus Q2, right? We are going to do that. It's slightly different than what it's here. Okay, and what I'm going to do, I'm going to break down this into two terms. Q1 and Q2. Yeah. Q1 over V plus Q2 over V. Q1 over V is C1, right? Just like you have here. And Q2 over V is C2. And look what we end up getting. We end up getting that the equivalent capacitance for capacitors in parallel is going to be the sum of the two capacitances. Compare that to capacitors in series, right? For any capacitors in series, you already know that that's the relation. For any capacitors in parallel, you're going to have this relation as well. And once you get to this point, you will be able to figure out how to get the equivalent capacitance of a network of capacitors, a combination of capacitors that are either in series or in parallel. Let's do an example like that. Okay, what you see here is an example that's in your book. We have a network of 3 capacitors, and they're not connected just in series or just in parallel, but they are connected in series and parallel. Okay, so here you go. You have an electric potential difference applied here by your battery. Okay, and then you have this capacitor here that are connected. Clearly, they are connected in parallel because those two ends here, the end of this capacitor plus the end of this capacitor, and those two ends are connected to each other. So they are clearly in parallel. So we can recognize that those two here are connected in parallel. Again, no? We recognize those two capacitors are in parallel, and we can go to the next drawing showing that showing the equivalent capacitance of those two, right? And that's what it is. Capacitance of C and C1 connected in parallel with C2 results in a capacitance of C12, which by the way is going to be 12 plus 5.3, right? 12.5 plus 5.3 would be 17.3. And now everything becomes clear, right? Clearer. Because now that combination of capacitors is in series with the third capacitor and becomes C123. Because they are in series, you have to take the inverse of each value, the sum of the inverse of each value. The final capacitance C123 is going to be less than 4.5. And that's what we got, 3.57. So that's what we get for the equivalent capacitance of this capacitor, okay? Now let's do something different now. Knowing that we have this capacitance, and then let's give a value, a voltage value for those two end plates of the capacitor. Let's say it's 12.5 volts, the voltage here. What we want to do is to find the voltage and the charge in each of the capacitors, okay, that we had initially, in each of the 3 capacitors that we had initially. Okay, the first step is to recognize that since we have those 2 points are kept at 12.5 volts, and those 2 points are in parallel to this capacitor here, it means that the potential difference between those 2 plates is going to be also 12.5 volts. If I call the equivalent capacitance as being C123, I'm going to call the electric potential between those 2 points V123. Okay? But remember, I want to get the equivalent capacitance of each of the 3 original capacitors, right? Not only we want to get the electric potential, right? Difference for each of the 3 original capacitors, not just the electric potential, but also the charge as well. So what we do, we will have to walk back what we had before. Okay, before this configuration, we had 2 capacitors in series, right? But wait a minute, we have the electric potential, but then we have to calculate the electric charge. The electric charge is going to be C times V. C 3.57 times V should be 44.6. Okay? Using the equation Q equal to CV. Now we have to break down this capacitance C123 into capacitors C1, 2, and capacitor C3. That's what we have here. Remember that? We're walking back what we had before. Capacitor C3, we know that has a capacitance of 4.5. C12, we know that has this capacitance here. Okay. Because the 2 capacitors are in series, we must have that their charge has to be the same as the charge of this original, of this equivalent capacitor. If this capacitor has this charge, Q123 has a charge of 44.6, each of the two capacitors, C12 and C3, we will also have to have this charge 44.6. Now that we know the charge, we can find out what's going to be V12 and V3, right? Just by using the definition of capacitance. Let's do that. Here you go, V12 and V3. That's going to be C, that's going to be Q divided by C. Q12 divided by C12, Q3 divided by C3. Okay. The electric potential difference between those two plates within this capacitor is going to be more than the electric potential difference within this other capacitor. Why is that? Because the capacitance here is greater than the capacitance here. Now, we do know that this capacitor is two capacitors connected in parallel, C1 and C2, right? And that's what the next configuration is all about. Previously, we found out that the electric potential between those two plates were 2.58, which means the electric potential of capacitor 1 and capacitor 2 will also be 2.58. 2.58 here and 2.58 here. Now that we have that, we know, right? Originally, we knew that the capacitance C1 was that, capacitance C2 is that. Now that we know C1 and V1, we can find out what Q1 and Q2 is all about, just by using the definition of capacitance. And that's what you see next. CV, C1, V1, C2, V2. Okay? And that's what the solution we have for this network of capacitors. You know, there are other combinations, possible combination of capacitor, but we're going to, stop it in this combination here that we just covered. Okay? What we want to do next is to find out how to calculate the energy stored by a capacitor. Okay? That's what we're going to see right now.